Welcome to the Dementia Researcher podcast. Supporting early career researchers throughout the world and across the galaxy.
Welcome to the Dementia Researcher podcast. I'm Associate Professor Yvonne Couch and I'm an Alzheimer's Research UK Fellow at the University of Oxford. Now, my normal field of interest is neuroimmunology, or how the brain, and in particular the brain's vascular system, copes with brain injuries like stroke. So today's topic is a little out of my comfort zone, but I found the background reading for this so fascinating, I ended up seriously considering a change of field. I'm joined on the podcast today by some amazing guests. We have researcher and author, Professor Christopher Mason. Professor Mason is one of the people behind the landmark twins study that followed identical twins, Scott and Mark Kelly, while one spent a year on Earth and the other spent a year in space. He works with NASA and is a researcher at the Consortium for Space Genetics at Harvard Medical School. Chris has also written a fantastic book, The Next 500 Years, about our future in space. Next, we have Dr. E.O. Whiteley, space psychologist, director of the Centre for Space Medicine at Mullard Space Science Laboratory at University College London. Dr. Whiteley worked with cosmonauts at the Gagarin Cosmonaut Training Center in Russia and at the European Astronaut Center in Germany, designing training for astronauts. He has written a book for researchers and practitioners, Toolkit for a Space Psychologist, to support astronauts in exploration missions to the Moon and Mars. Her latest papers focus on how to detect invasive fatigue in astronauts, and she explores our inner space whilst we explore outer space with the aim to develop our abilities and realize our potential right from birth. Finally, we welcome a guest many of you have heard from before, the wonderful Professor Henrik Zetterberg. Professor Zetterberg is Professor of Neurochemistry and Neurodegenerative Disease at University College London and the University of Gothenburg. He is a leading expert in fluid-based biomarkers in dementia, and in 2020, he discovered a new method to detect the disease about 2 decades before significant symptoms are present. In today's podcast, we will be exploring the effect of space travel on the brain. This is an enormous topic, so to break it down into manageable chunks, we're going to talk about the 5 major hazards of space travel: radiation, gravity, isolation, environment, and distance. Okay, hello everyone, and thank you so much for finding the time to join us today. So let's leap off with a bit of background on you guys, because whilst most of our listeners might be familiar with research in space is a bit next level. So could I maybe start by asking how you found your way into your particular research field? Chris, how about you go first?
Happy to. Well, thanks for having me. I really have been always curious about genetics and space since I was a kid. And when I actually first started my lab at Cornell, the very first grant I wrote, because you get some money and they say, go forth and be productive and write grants and papers and discover things is generally what the university tells you to do. I actually wrote to NASA and said, there's lots of precision medicine and genomics being done for patients on Earth. But what do we know about really the changes when you're in space? And arguably one of the highest risk environments for any human being to go into. So I really sent them a proposal and said, I don't need any money. I just needed to get samples. And they said, well, we don't have a lot of banked, purified blood samples or viably frozen cells, not yet, because they just started talking about expanding that work. And so then they announced that they were looking for ideas for a twin study. And I said, oh, great, I've already got the grant written up and sent it in. And we were one of the 10 teams selected there. So it was really, and I've done a lot of follow-up work since, but that was kind of the first jump into the field and led to a lot of great collaborations on looking at the molecular side, the genetic side, cognitive changes, everything we could measure about the human body in space.
Excellent. Thank you. And we're definitely going to leap in and quiz you about the twins a little bit later in the podcast. How about you?
Thank you. Thank you for letting me join this lovely roundtable discussion. I have started also from very young age. I wanted to fly and be in space and see how it looks from above. I couldn't quite get into flight school because they were not selecting women at the time. So I thought, not a big loss, I'll jump with a parachute instead. And So, and then it went from there. I knew that I need to take little steps. So I went to study how pilots, how to assist pilots in absorbing information in short amount of time and without kind of making mistakes in the process. And I thought that will help me to understand what people are like in extreme environments. And I was working with military crew in Australia. They were converting C-130J Hercules. So this is like a massive cargo plane designed by Lockheed Martin, from an older analog version with dials to displays, so like glass cockpits full of screens. And I wanted to understand what are they thinking, what are they doing? Because the pertinent question is that how do people know what to do and make the right decisions at the time in extreme environments when they're in absolute pressure? They've got, the time is always on them, kind of. And one thing that I've learned as a pilot of a light aircraft, is that you always have to stay ahead. So every pilot that you speak with, and in fact, every cosmonaut and astronaut, are always ahead of their flight. So they know and they pre-calculate the situations that are ahead of them. And that's how they are able to stay ahead. And of course, when the crisis happened that, for example, they haven't, able to foresee, they have so much training that behind them that I've heard from astronauts saying that when they walk towards the rocket, they feel like superheroes because they think there's nothing, absolutely nothing that actual real situation can throw at them that instructors haven't, because they literally take every aspect in training to consider what could happen and will never happen, but they throw it at them anyway. So they feel prepared. And I think that state of preparedness is what I'm fascinated about. How can people be so present, in the moment? How do they get to that state? And that's what I wanted to study. And from pilots, I went to apply for various research in space, and that's how I'm doing this work.
That is absolutely amazing. I'm very jealous that you jumped out of a plane. I really want to do that at some point. And flying less so, I think my brain is I don't think far enough ahead to be a good pilot. I'd be terrible, but I would like to jump out of a plane. I think that would be incredibly fun. So Henrik, I know you mostly focus on dementia. How did you become interested in this topic?
Well, I got an email. That's the whole explanation. So basically, what we have done is that we have I sort of adopted something I call opportunistic study design. So we have developed biomarkers for brain diseases for many years, and many of the methods we developed were sensitive enough for cerebrospinal fluid samples, but not good enough for blood. But then eventually, since 10 years, we have slowly worked ourselves against towards having the analytical sensitivity to be able to measure proteins that come from neurons in blood. And then when these assays came about, I started to think about different scenarios where we could look at brain stress in different ways. And so we have studied the dynamics of these biomarkers in boxing, in mixed martial arts, in soccer or football when you head a ball. We have looked at breachers who break into rooms using high explosive gears and such things, where the brain could theoretically be impacted by different forces. But I never thought about space research until a neurologist who is an expert on how the brain reacts to microgravity, how he basically emailed me and said that he had access to samples from Russian cosmonauts who had been on the International Space Station, and he had the samples before and after they came back from this. And his idea was basically to look at what microgravity would do to brain health. And he had clinical measures that after you land from this extended time at the International Space Stations, these cosmonauts were there for almost 6 months. And then cognitive scores are quite poor, and it takes time to recover. It takes time to recover the whole body, but it really takes time to recover brain function also. And basically, he had access to these samples, and he asked us if we wanted to measure them. And what we did then is that we measured the biomarkers we have developed for neuronal injury, astrocytic activation, and also some other proteins that relate to aggregation of some of the aggregation-prone proteins, for example, beta amyloid that form clumps in the brain in Alzheimer's disease. And we got quite striking findings because all these 5 cosmonauts display the same biomarker changes in their blood, indicating that either neurons were injured and or the clearance mechanisms of breakdown products from neuronal metabolism that they didn't work up in microgravity as they should, and that is it's these are pilot data, I have to admit, but it looked quite interesting, and I think this could be of relevance also when we talk about space tourism and such things.
Definitely. And that, I think you've highlighted one of the really interesting sort of future directions in this field for me, in that we need to get more samples and we need to figure out what's going on with these people when we get into space. But like I can go down the corridor and stick someone in the arm with a needle and get blood, but doing that in space, I think is really challenging, and getting things like CSF, which would be amazing, is going to be, I think, really difficult going forward. But let's get right down to business and start with some of the hazards that people might experience when they travel into space. We're going to talk about radiation and gravity first. So Chris, can you tell our listeners a little bit about the kinds of radiation astronauts might expect to experience when they travel into space?
Yes. So it is not pleasant for the body in terms of the amount of radioactive particles and high energy particles zooming through your body. It is equivalent to generally having about, say, 3 to 4 chest x-rays per day if you're in low Earth orbit, is kind of the way we often think about it. And that is, so it gives you then an effective radiation dose over time, which is often measured in millisieverts. And just to give you an example, when Scott Kelly was in space for 1 whole year, it was about 146 millisieverts of radiation. And so that's a fair amount. Actually, if you go to Mars, though, go to Mars and back, it would probably be around 1,200 millisieverts. So it might be anywhere from 8 to 10 times more radiation. A lot of that is because as soon as you leave the low Earth orbit, you're outside of the Van Allen belts, you don't have the protection of Earth's magnetosphere to kind of shield you. And so even though you're getting more radiation in space than you would on Earth, it is, it's not, nothing would hold a candle to what you get to, say, Mars and back, or even some of the lunar missions. And so what that does is, when you get irradiated, but to be fair, you can get, the equivalent of this is if you say, well, how much would I normally get if I'm on Earth? The background radiation, from what we've seen, if you, for example, go up in space, the Inspiration 4 crew we just looked at, so if you spend about 3 days in space, that for them, they were at a slightly higher altitude. It was about the equivalent of 9 months being on Earth in terms of how fast you accumulate that amount of radiation just on Earth. Because again, there's uranium in the rocks, there's radiation all around us. The Van Allen belts don't protect everything or the atmosphere, but it is, so what we see for the manifestation of that radiation in space is you can actually see breaks in the DNA coming out in the blood, also in urine for the astronauts. There's a modified nucleotide called 8-oxoguanosine, which is a damaged base, one of the letters of our genetic code. You can see it come out in the urine of astronauts. We've looked at 59 astronauts. It happens to all of them in flight. You can actually see the body sort of ejecting these damaged bases. You can see it in the blood as well. So we know that they're being irradiated, but we can also see it in the way their genes respond. So a lot of the activity inside of the blood cells, you can see the DNA repair networks all activating and quickly coming to life to say, aha, I have to repair this broken DNA, which again, we do all the time on Earth anyway. It's much more active. And for the most part, it does a pretty good job. We actually have looked at measures of what's called clonal hematopoiesis, or where you can have clones of blood, clones of mutated cells that are in your bone marrow in your blood, and you can see if they change. We've actually seen that some of them went down even in space. So some of the mutations that Scott had got a little bit better in space. Some of it's because he's, working out every morning, eating very healthy, getting a good night's sleep. and in some ways having a bit more of a healthy lifestyle. And his telomeres got a little longer in space, which we've now seen in 11 other astronauts. It seems like an unusual, usually longer telomeres means that you're younger. And so in some cases, we think it's almost this low dose radiation is kind of priming the immune system, priming cells that were close to being dead to being kind of shuffled out of the body. And so it's both good and bad. You're being irradiated, but it might not be at a necessarily too dangerous level or speed. But we're still, studying this with additional astronauts. That's a quick summary of those findings.
Well, long term, just to jump in on that one, long term, if you're being irradiated that much, how many of these astronauts have been studied sort of over a really long period of time, sort of like tens of 20 sort of years length of time? Is this going to affect their, chances of getting cancer or things along those lines?
Great question. So far, the answer seems to be mostly no. They do have a slight enrichment for some more rare cancer types, but there's really, there's only just over 600 people have ever been to space. About a third of them are Russian, so we don't have their data, and we don't have that much genetic data on even the astronauts we have. So far, and they're also very healthy. They're a really healthy stock. But what's really interesting is we're now starting to see more civilian crews go up that are normal Joes and Janes going up into space, like we just saw. And so we did the same protocol for the Inspiration 4 crew that we did for the twin study. We're doing the same for a lot of the Axiom missions coming up. So I think we'll start to have a better sense of that. If you're just a normal person, not a demigod that's going into space because you're crazily healthy and fit, what will that look like? So we'll begin to understand that in the coming, I think, years.
So if we bring it back to the brain, Henrik, on a cellular level, what do you think these kinds of radiation and these kind of stresses are going to be doing to our bodies, but also to our brains? What's going to go on in terms of your brain cell health?
Yeah, in terms of irradiation, I'm not that worried about the brain, to be honest. Although, of course, this is it can have the same effects on DNA integrity as Chris just mentioned. But I think actually that what we saw, if I interpret the data again, remembering that it was just on 5 people, but with the same pattern, to me it looks like the clearance mechanisms of waste products from the brain into the blood are disturbed. The mechanism is not clear, but in the brain we have something called the glymphatic system that operates to remove metabolites from the brain. And that glymphatic system is dependent on a diurnal variation and also passive and slow flows of fluids. So the interstitial fluid that bathes the neurons is cleared throughout some almost like paravascular, close to the brain vessels, the blood vessels in the brain. The interstitial fluid is flowing, bringing metabolites from the brain and emptying itself in to the bloodstream. And it looks like when people have landed after having been in space, it looks like this system starts to work again, and then all these molecules that are brain derived, they come out from the brain, giving higher blood concentrations. If these proteins build up in the brain and accumulate, there is a risk of getting these type of protein accumulations that we see in neurodegenerative disease, but no one has seen a clear increased incidence of dementia or something like that in astronauts, at least not to my knowledge, although acute cognitive dysfunction has been seen. So I would say that I think this is more related to being in microgravity than irradiation, and it's also it could also have to do with disrupted diurnal rhythm and sleep patterns, because one fascinating feature of this glymphatic system is that it opens up and becomes most active in deep sleep. And if you don't have the possibility of having prolonged times of deep sleep, which can be hard in space, then this could potentially impair the clearance of these proteins. Deep sleep is super important. I mean, if you don't sleep at all for 1 or 2 nights, that will work. You will work, but you won't feel that well. But after 3 or 4 or 5 nights, then you start to get problems. And sleep is not an easy thing for astronauts. And of course, there are things to help with medications to make that work better. But if that is also in combination with microgravity and fluid dynamics, then that is a little bit more complicated. But potentially one could do something about it, which is one reason for why both NASA and the Russian Space Agency have been interested in this.
It sounds like a perfect storm of awful things to be happening to your brain all at once. But we will definitely talk about lymphatics and sleep more in a little bit, because I want some of Ia's opinions on that as well. But we know that radiotherapy, so if you have radiotherapy for cancer, we know that that can affect you cognitively if you have that sort of over a long period of time. And Ia, I'd be keen to get your opinion on this. If we've got serious changes in areas of the brain, like the hippocampus, that might affect memory, and areas of the brain that might affect risk-taking, what kind of behavioral changes might we expect in people who are going to space for prolonged periods of time?
I wanted to comment on what Henrik was saying regarding sleep, and that's related to memory. So I've been fortunate to participate in training rather than a study that is conducted with Russian cosmonauts. And part of the training is sleep deprivation, which is extended, so over several days, 72 hours. And what happens is that once, of course, there were some of the medical studies been done, but I have not participated in that. And of course, the date is closed. But what was interesting is that what we saw, that once people started to have less and less sleep, such as accumulated fatigue over time, their memory deteriorated, the short-term memory, and they were unable to follow simple instructions. So for example, if you are in an accident or an emergency, they will only for sure be able to follow one step rather than, for example, a 3-step procedure. However, their long-term memory kicks in. So for example, if it's an emergency and they need to perform 3 steps that they remember, that just springs up quite quickly, because it's also a body memory, such as what they do in training. So that's interesting, that of course the memory has a big impact, especially short-term memory, when you have to react to things and you have to work as a team and know who is doing what is doing. And little bursts of sort of chemicals to set you off, for example, because you are in an emergency, could help you, but very short term, and it exhausts you faster as well. So that would be my comment on the memory.
Yeah, and I think that's really important. And like you said earlier, you've almost got muscle memory for so many different protocols that you've got to go through. But if you have to sort of spontaneously react to something random, if you're sleep deprived, you're going to be almost much worse at doing that. And I think that's something that's going to be really interesting in terms of training people going forwards. So we know that radiation is a serious threat, but for me, this is where it gets interesting. So the perceived risk level for radiation exposure seems to be different for different individuals. So women are more prone to develop things like cancer than men. Smoking and obesity will alter your risk. Age is going to play a factor. All kinds of other things are going to play into how radiation affects your body. So Chris, does this mean we need to really carefully select crews that we send on longer space missions? And what factors do you think might need to be considered? And, do you think the current selection process that we have is the right one? Like you said, that we're selecting demigods. Do you think we should be selecting demigods?
To make space more accessible to people, we will inevitably have to broaden the scope. And if the Starship starts sending people to Mars, 100 people at a time in the next 10 years, in theory, it will probably include a broader range of people very quickly. So I think what's currently used is a very rigorous procedure that includes, the most healthy people, and that pass a wide battery of tests. But to your point earlier, women have at least based on the NASA recommendations, have a lower acceptable limit for radiation exposure. And a lot of this is based on data from survivors of Nagasaki and Hiroshima from some of the atomic bombs that were unfortunately dropped there. But we, learned a lot about what was the incidence of cancer as a function of age and sex. And that, but there are, new mitigation strategies that you could deploy. So radiation countermeasures are not just tablets now. You could even have epigenetic therapies that can be used to prime sort of your DNA repair genes, is something that DARPA is looking at, the Defense Advanced Research Projects Agency here in the United States. So there's work being done to try and think about other ways to address that challenge for sure. But it is going to be harder to make sure that people that are older or more obese, or William Shatner just made it past the Kármán line, and he's 90. So there's a much broader range of people, both older and younger, going into space in the past 10 years. But I think it's a good thing. It's like any clinical trial. You start with a small group of people. You learn what you can. You learn a lot more when you broaden it to phase 2 and phase 3 clinical trials. We're basically in the clinical trial of humanity, and the trial is space. So we're just in the early stages of figuring out the response to a broader range of humans. But we're learning for sure a lot. I think even actually to Dr. Zetterberg's point, some of the peptides we can see even in exosomes, we've started to see, like in the brain, how it clears proteins in the brain. Some of them showed up in the blood of Scott Kelly when he got back to Earth, which is the first time we've ever seen brain-derived peptides show up in exosomes that were in the peripheral blood for any of the controls or other astronauts. So we can start to at least measure some of these changes, and radiation risk, and get dosimetry down to the cellular and molecular level, which is helpful, that measure of radiation risk. So, but it's going to be broader. It already is broader, and I think it will continue to broaden, which is good for the clinical trial of humanity in space.
Definitely. Incorporating a lot of noise, I think, is good if you've got a decent enough signal, although I'm now extremely distracted because you said exosomes, which is one of my favorite words ever. So now I know my into this field. I'm going to leap. I'm going to find someone who does exosome research in space, and that's it. I'm ruined. I'm sorry.
But there's only one paper. We have one paper, but I think it's the
Excellent.
only one. So
right. I'm paper number 2. That's it. I'm sorted for the next year and a half at least. But you mentioned William Shatner there. So Henrik, I'm going to jump on you for this answer. William Shatner is 90. Do you think that cells in an old person's brain are going to be different, and how are they going to cope? So you mentioned the lymphatic system and that the drainage might be different in space. How is that system different in an elderly person, and are they going to cope with the changes of space different to a younger person?
If we start with radiation, actually, medically, we often allow older people to get more radiation because you won't have that much time to accumulate additional damage. So it's so that is so perhaps it's good from a radiation perspective, I don't think we have to be very careful with the older people, but from brain physiology perspective, older brains at group level work a little bit less efficiently with clearing, for example, debris or metabolites from the tissue, and that is mostly related to stiffening of the small blood vessels of the brain, and they really make up this most important part of the lymphatic system, which involves dynamics in how well these paravascular spaces alongside the vessels open up when you enter deep sleep, and that type of flow from the brain interstitial fluid into the blood starts. So I think from that perspective, older brains could be a little bit more vulnerable to changes imposed on the brain by microgravity, and also this type of additional disturbance of the circadian rhythm and diurnal variation in sleep patterns and so. And I mean, that happens with normal aging also. The sleep gets more disrupted, and that has been in some individuals, and that has been hypothesized to be a little bit of a risk factor for neurodegenerative disease. I'm actually not super worried about about older people in space because of this fact that they might have a shorter life to live and might not have those. I mean, the brain changes in old age are not super acute, but of course you have to be cardiovascular and muscularly fit. That will be important. I more think about younger people who, and if it becomes common to go and stay up longer, and or having, one thing I would be very interested in is to do a study to examine if longer time periods in space are better or worse for the brain and this type of brain dynamics changes than which one is worst. I think we now have the tools to determine that, and I think we should study that.
Yeah, and I think if we are thinking about going, well, I know that there's the mission to go back to the moon, and I think if we are thinking about going to Mars, knowing more about how these long-term exposures affect the body and affect the brain, I think are really important. So you touched briefly on, we've touched a lot on fluid dynamics and the potential effects of gravity and microgravity. So Chris, can you give our listeners a brief primer on the differences between gravity, microgravity, and zero gravity, and when the astronauts or the cosmonauts might experience each of them?
Sure. So there's often there's a big debate in whether we should even call something microgravity, because we don't have a way to measure the exact amount of gravity you're getting. We just know that as you move away from a large objects, you have NASA calls it altered gravitational fields, often instead of microgravity, because we don't have a gravitometer, or that we can say you have 68 gravitons that you now have, right? So there's no, and if anything, it's actually the experience of microgravity is just a continued falling towards Earth. And so you still have Earth's gravity very close to you relative to the size of the object. You actually have really almost the same amount of gravity that your body experiences. It's just that because you're falling towards Earth, you have the experience of microgravity or zero gravity. But I know several people at NASA who don't even use the term microgravity because they so despise the imperfection of the term, because again, it's a huge object. It's a planet, right? You're actually not that far from it. You still have all the gravity. You're just falling towards that planet. And so that experience is just a consistent falling, which of course you can get in a parabolic flight where you have the exact same feeling of zero gravity, but for 15 seconds at a time. But then you get it back again very quickly. So I think they're used synonymously, though. Zero gravity and microgravity are often used in conjunction, but fundamentally, when you think of where your body is in the universe, you have almost all the same amount of gravity. It's just that you're falling towards a large object, which is what we call zero or microgravity. So it's kind of a funny misnomer that's used broadly, I'd say.
Yeah, we're putting labels on something which is not currently measurable, which is right. A very sciencey thing to do. We must label everything. So I'm going to come back to you in a minute to talk about the long and short-term effects of gravity on the body. But yeah, I'd be keen to know your thoughts on the psychological effects of gravity. So you're going up in space, and everyday tasks are suddenly done in, I want to say, almost like an extra dimension. So you're suddenly having to learn how to put things down and pick things up and drink things in midair. How quickly do you adapt to that? Like, what stresses does that kind of environment put on a person psychologically? How do they adapt, and how quickly do they sort of de-adapt when they get back to Earth?
Well, I had a fortunate to speak with cosmonauts and astronauts about arriving to the station to SS, and one about a week for about a week, depending on individual physiology, that it takes time to adapt. So of course, all your fluid shifts up, so you feel like you have a cold, and your senses, like for example, tasting buds, because of your tongue enlarges as well. So it's like you're having a head cold, essentially. And you have to still perform at the top of your ability. And you might be hit with this for the first time in your life. And it's continuous. So of course it is straining, but they have a larger goal in mind. And as I mentioned before, they're looking to perform their best. And they trained and probably dreamed of this since they were very, very young. And so one interesting interaction that I found is that when the crew, when they first arrive and they're trying to reach something, so for example, if you go with your hand to reach something and it should be pulled by gravity here, so they always overshoot upwards. So when they're trying to reach something ahead, and of course your brain adjusts, so like the experiment of riding the bike with the reverse wheel, with regulation of direction is different, or the reverse. So it's the same thing, is that it takes time to adapt, but then you do. And there are many functions like that you do, and then you just love them because they are different to Earth. So they become like children. They try to understand how it works and what to do, and they play with that. And that's quite humorous. I found that in the military and in space personnel, they have a lot of humor. And that's what saves the day and tension and difficulties. So they always find the way to make a laugh of something. And that what helps psychologically to adapt as well. And of course, more experienced cosmonauts and astronauts make jokes on the younger ones. So there are little tricks.
I think what you said there is really important. I think having a sense of humor and having some innate curiosity about how things work. And I think that's with gravity. So you can study so many extreme environments on Earth, like Chris mentioned, Nagasaki and Hiroshima, and we've got sort of areas of very high radiation on Earth. We've got extreme isolated environments like the North and the South Pole where people can go and experience that kind of isolation. You can't really do microgravity or zero gravity. You can't really do that here. So that's the sort of thing that they're going to experience for the first time when they're up there and have to figure it out along with all the other stuff. So I think that's the fact that they've got to do that on top. The description of them as demigods, I don't think is unwarranted. But one of the major effects that gravity is going to have is on the fluids of the body. And Henrik, you've already mentioned the lymphatics a couple of times, but take it back to basics for our listeners. Can you tell us how fluids like blood and lymph are normally kept in their various compartments?
Yeah, in the brain, you mean?
Yes.
Yes. So one could. There are a couple of important fluids that are a little bit specific to the brain, and one is cerebrospinal fluid, which is a filtrate of plasma, and that fluid is made inside the brain by something called the choroid plexus. It looks like grapes almost, and they produce from the blood is going into these grapes, and then it's filtrated and released on the brain side into the ventricles of the brain, this clear fluid which to 80% is composed of blood proteins. This fluid is communicating freely and moving around in the brain with the brain interstitial fluid, and that dynamics is driven by the heartbeats. So if you're in a neurosurgical setting and you open up the skull, you will see the brain move, pulse synchronously. You can also feel that if you have been out late at night and the morning after, you can feel those movements of the brain the day after, and it's really that really drives the dynamics of and moves the fluids around and mixes the interstitial fluid around the neurons with the cerebrospinal fluid of the ventricles. This fluid is also then driven pulse synchronously, slowly along the spinal cord down to the lumbar sac, and there we can sample it. And then it also goes up over the hemispheres and empties itself into the venous blood system through something called granulations, arachnoidal granulations. That's one part of these clearance mechanisms. This fluid doesn't bring nutrients, but it really removes waste products. Then we have of course the blood vessels of the brain that brings oxygen and nutrients, much like the blood is delivering these important things to other cell types of the brain. But the coolest thing with fluid dynamics of the brain is this lymphatic system, because it has been known and described like in the 80s. But Michael Nedergaard, who works in Denmark and the US, she sort of rediscovered it in rodent models, and she really characterized it deeply with her team. And then what she could see was that if you follow a rodent and fluid dynamics in a rodent brain over 24 hours in the light dark cycle, you can see that there are spaces opening up in the brain along the blood vessels when animals go to sleep, and especially when they enter this type of deep sleep that is so important to humans. And this is really something that seems to move fluids a lot along the brain parenchyma. So then we have cerebrospinal fluid, which covers the hemispheres and also are in the ventricles. But this subarachnoidal cerebrospinal fluid, which lies on the brain, when you enter deep sleep, it is sucked into the brain. And then when you wake up, it moves along these blood vessels and empties itself into the blood system on the venous side outside the brain. This really seems to be an important and evolutionary conserved system. And I think this explains, to some extent, I don't think it explains all about why sleep is so important, but it explains a large part of why deep sleep is important. And why this has been evolved to work like this, I do not know, because I mean, sleeping must be a little bit dangerous if you are at the savannah or so, but we really need it. And you can be awake, as Ia said, one night, you can be awake 2 nights, but if you do not get any sleep for 3 or 4 days, then I mean, that's torture, and then you will experience acute brain function breakdown. That's really the case. I do not know if anyone has described this in space on any of the cosmonauts or astronauts that have been up there. I'm ignorant of that, but perhaps someone else knows.
Well, one question for deep sleep: to get deep sleep, you need at least how much sleep do you need to get to deep sleep? I guess if you can clarify, I guess
it's such an important question from a personal perspective. Also, you need 4 hours, and a healthy brain. If you are sleep deprived, I mean, if people are, and perhaps this is a little bit individual also, so perhaps there are people who need less, and some people, I mean, most likely it is like this. But if you are healthy and you are sleep deprived, I mean, many people who listen to this will have had such experiences, and some have perhaps kids and can't sleep at all, they think, but at least you get some hours, and that's enough. If you are sleep deprived and what happens to the sleep patterns is that you prioritize deep sleep. So you dive down into deep sleep, which is dreamless. So the brain or the body prioritizes the deep sleep to get that clearance mechanism. So I don't think it's dangerous to be sleep deprived. I don't think it's acutely dangerous as long as you get 3, 4, 5 hours. I mean, then I think you can live with it. But you will have a little bit of a problem with synaptic homeostasis and making new memories and such things. And perhaps during these, if you have experienced prolonged times with sleep deprivation, often people, when they talk about those times, it is a little bit tunnel-like. It is not. It can actually be that you have a quite vague memories from what happened during that time, and that you also can experience in deep depression and psychiatric diseases.
Chris, I was going to jump in and ask you whether you knew anything about what happens to the circadian, because I read somewhere that astronauts experience up to 16 sunrises and sunsets a day. So what happens to the circadian rhythm of someone who's in space, and is there any way of like helping them get regular sleep in that maybe isn't drugs?
We do see a lot of certainly the gene expression patterns. Look at what genes are going up or down, which normally they're very beautifully cyclic. You can see, these sort of waves crashing on the cognitive shore in a very regular fashion, but it's almost completely disrupted, at least on a gene expression level. They do, since we see a lot of the genes not as cyclical, or they're adjusting, or they're differentially regulated. But the astronauts do, they sleep, it's like in a vertical kind of closet, and they close the door, and they try to, as best as they can, simulate at least the sleeping part of the day is dark, and they work a lot in the day. So as much as possible, their day is organized to try and keep it in something of a normal cadence. But they also have lighting that is used on the space station that changes the frequency of the light to simulate what is the light patterns over the course of the day, which also impacts cognitive function and health. So so some of those are just being developed and deployed on the space station, not in all the modules yet, but there's even some that's being put into office buildings, right? Like you want to have a different shift of red light and blue light at different parts of the day to try and simulate whether you should be waking up or sleeping. And so I think it's not good if you want to pull an all-nighter. Like if you have to jump into work for a 14-hour day, you want to have all the lights on maximum. But if you want a normal life that is, it's 8 to 10 hours of working on something, or maybe 6 to 10 hours, or maybe 4 if you're going to the beach in the afternoon, you want to have some semblance of what it looks like on Earth, because of course we evolved here. But they do what they can on the space station to match that.
Yeah, and I think there's always going to be those problems with things like jet lag, because presumably people are going to the space station from all over the place, so their rhythms are going to be all over the place anyway. Henrik touched on sort of depression and things that can be affected by this change in circadian rhythms. And Ia, I'd be keen to get your insight on whether you think these changes in sleep patterns can affect the emotional state of people going in space, and whether we might expect different changes on longer space missions. And do you think there's anything we can do about that?
Yes, of course. I mean, as soon as we are sleep deprived, and we know that if you have small children, your patience goes down radically. and hence, when we are unable to function happily then in our daily life, because we just have to pull through rather than enjoy the day and having time to enjoy a conversation or a thought or appreciate where you are. If those moments are missing, then our emotional well-being goes down as well. And yes, of course, in Mars 500 study, which I've been also participating as a researcher, you could see that the crew, after a while, they've exhausted, I guess, the conversation. And of course, that was specifically designed to observe what happens to the crew. And we know that in Antarctic missions as well, because they're very much an analog to long duration travel. So the best thing is that the crew prepares and they know about it, they talk about it. The best way to be prepared is to converse about who is like, how every one of us is like, in what kind of situation. And the book I published, what Toolkit for a Space Psychologist, actually maps out the situations and categories and factors that the crew can go over in a training scenario in preparation for long duration missions or a short duration but critical missions. And they're able to discuss it and see what kind of reactions they're expecting from others, and also think through what are they going to be like. So by talking through it and thinking through that allows you to be prepared. And of course, they do know that they will be there for a long time. So, and astronauts and cosmonauts are highly driven individuals. They always want to learn. They are continuously learning something, because in space, there are some of them not even 5% of their entire career of their working time. So they're doing, they're supporting the crew on the ground, they're supporting the research, they do administration, they do public speaking and so on. So they're continuously learning, they're learning languages. So they all prepare, they have a list, to-do list they've always wanted to do. And they will take that with them on a long duration mission. So I don't think for people who are striving forth have the problem of being bored. There's always something for them, they're leaving with the list of things I want to do when I have a moment.
Yeah, and I think that's going to be really important. If we're going to send people all the way to Mars, you don't want them going stir crazy on the way and going postal in a spaceship. I think that would be an ultimate disaster. But on that front, Chris, you've got this wonderful 500-year plan for the human race, but let's break it down for everyone. How long do you think before we go to Mars, and how long is it going to take us to get there?
So I'm hoping that, some of the missions I talked about earlier on this podcast is that, we might be there within 10 years. Actually, China's stated they want to get there by 2031 or 33. NASA's saying 2035, maybe 37. But it all should be within the next 10 to 15 years if all goes according to plan. Of course, Mars is far and it's difficult, but it is possible to get there and hopefully return back. We, I think the 500-year plan, I just published a book this year. It's called The Next 500 Years, which is about not just the missions that we've done so far, but also engineering life to reach those new worlds of, one of the therapies I mentioned briefly is even epigenetic therapies, where you turn genes on in advance of a threat like radiation, which is being tried right now in mice and in cells, but could be done in humans. But also underscore a lot of the genetic engineering trials that are happening today in humans for targeted work with CRISPR therapies, where you can actually cure beta thalassemia or sickle cell disease with modifications to somatic tissues in your body, or not your egg or sperm, but just curing a disease in a body today. So I think, given a lot of technologies that some clinical trials we've helped with and that are elsewhere, it is really important to imagine a future that is, if it's 10 or 20 years from now, you could imagine other ways to keep astronauts safe. And I argue that in the book, ethically, you might have to, because if the alternative is we send people to Mars, but they won't survive because there's too much radiation, not enough resources. But if we could give them a little bit of a boost internally as well as externally, maybe we should consider that. It's kind of the thesis of the book. And also it's an argument that we have to explore other places in the universe, because we're the only species with an awareness of extinction. So we're the only ones that can prevent extinction anywhere in the universe. As far as we know, it's just us. So I think it gives us a duty for our species to actually protect other species as well as ourselves. But in the next 500 years, it'll be in the next 10 to 20, it'll be probably getting to Mars. And then with some of those engineering tricks, could maybe get out to the other planets in the solar system by 2150. The goal at the end of 500 years is to know enough biology and science and engineering to build a generation ship so we could get towards another star and eventually have a planet in the habitable zone, get out to another solar system is the goal of the plan. And I just detail all the technology and lessons we learned from previous missions. Plus, at the end of the book is a list of every planet and exoplanet that we could possibly go to today. That's a few parsecs away, so it's not too far. And then it ends with the end of the universe, the last of it. So I ended what would happen at the end of the universe is the last chapter, which was kind of depressing, but we don't know. It's a long ways away. We've got trillions of years, but it's a long ways away.
I like the forward planning that you're going with there, though. It's important to think big.
Yes.
But if we're going to go to Mars, it's going to be a long trip. Ian's already mentioned that the crews that go on these missions have this sort of, lifelong to-do list of things that they want to do. So, they're not potentially likely to get bored on a longer mission. They can, learn French or whatever it is that they've always wanted to do, play the sitar. Henrik, this is a question for you. So it's sort of linked to neurodegeneration. Do you think on these longer space missions, there's always this phrase, use it or lose it, in terms of your brain health? Do you think that's going to be important in terms of longer missions? If you just sit around in a spaceship and do nothing and don't learn the sitar, do you think your brain's just going to deteriorate quicker than it would if you were just sitting around on Earth?
Absolutely, yeah. So it's I mean, that's use it or lose it is a bit harsh perhaps, but it's definitely something we know a lot about, and I think Ia has a lot to comment here also. But I think that having a meaningful time on that spaceship will be essential, definitely.
And I think finding things to do on that long mission would be, I would love it. Somebody shut me in a box for 6 months and said, you can do whatever you want. I would have a fabulous time. But yeah, I've got a question for you on sort of the long periods of boredom and brain health and things. Do we think, so Chris has already mentioned that we've got these sort of demigods in terms of health and fitness and all that kind of things, nutritionally aware and super brainy people that we're sending on these missions. Is there a specific type of emotional or psychological personality type that we need to think about sending on longer term space missions?
This is a very well debated topic and question.
Like Myers-Briggs type analysis, or what kind of person? Yeah, what do you? Yeah, something like that.
Yeah. Well, I found in my experience, I've selected over thousands of people for Emirates Airlines, and I traveled pretty much on every flight that they had to the country, because they're selecting, or we were selecting from the culture that they were flying to. So they had to be on board a person who culturally grew up there and spoke the language in a native way. So they understood the peculiarities, because of course, we're talking about Muslim countries, and how you serve the food is a big deal. And of course, in flight, a lot of the activities that do happen is actually about serving food and being respectful to others. And so I found that when you're selecting cabin crew and people who flourish later, they're able to distinguish and adapt to the two different environments. So for example, if I tell them, would you please complete this questionnaire as if you are in a work environment? And then I would say, okay, now, after a period of time or even soon after, would you please complete this as if you are with family? And you would get different scores. Okay, and that's normal, and that's not cheating, it's just how we adapt and what we're comfortable to open up. And some people who are introverts might actually, go on the same spectrum, like we're all on the spectrum somewhere, right? So it's just what we are exerting in front of others, or when we're alone, we are secluding, and other parts of us come out when we're in friendship and more relaxed. And also there's cultural expectations, and that's all reflected. So when we were doing different cultures, so for example, for Thailand, and if you compare Thailand and Ireland, they were, the people were expectation on how they should be at work were absolutely opposite. And if you are interviewing them, because we did not ever, down selected just on the questionnaire, because that was becoming more and more obvious that people are different to what they're saying, on the questionnaire. They want to be liked, that's natural. So once you are in the interview and you're speaking with individuals and you say, okay, can you give me an example when this happened? Because I'm not sure how to interpret, for example, that quality or what they're describing. It doesn't seem to me, because I've observed many people, in situations, and we do like team play, and I'm watching and I'm checking, is the data there or not? So there's a lot of observational skill, and the expectation on how you behave in front of another person is so different. And also, if you go to Thai people who were the military pilots, they would be so different in how they command the crew and how they respect superiors, and all of that culture had to be changed as well through training. So crew resource management is something has been widely used in medicine as well. So it is a question that I don't think has the right answer. Of course, these are highly striving individuals, and you will see them succeed, and they know how to position themselves. And but I think the most admiring quality, and the one that works on International Space Station specifically, is that it's the person is willing to take a commanding position as well as following position, because the situation change and the expert might be not the commander, and they are aware of that. So that capability and that ability to change depending on the situation is what I would be looking for.
Yeah, so a high degree of sort of self-awareness and the ability to work well within a team as well as sort of independently, I think would be important.
Lead and follow, and you should be able to intuitively switch when, so that's about, I think, a key feature.
And I think that's something that someone like yourself who's very experienced in sort of watching crews develop, I think that's going to be the way to sort of pick people going forward. But Chris, you did the twin studies. I know it's a tiny n, it's an n of 1, but did you notice, and did you make any sort of psychological observations between the guy that was in space and the guy that was on Earth? Was there anything that sort of struck you in terms of their experience?
Well, they're identical twins, so they're very similar in a lot of ways, but they also, and they're very competitive, but they of course are different. And actually, one of the twins, when playing the cognitive game that was developed by Dr. Matthias Bosner at UPenn, actually learned how to trick the game after a while. So we could see that even how they, over the course of 2.5 years, and one of those years was in space for one of them, you could see how they learned the games differently. And their behavior was, they're very similar people. They're both astronauts. Could you imagine being at a Christmas party and saying, oh, well, both my sons are astronauts? And like people are like, no, really, they are. They both are. So they're both very similar, both very driven, but they respond even to cognitive tests and games differently over time. So we think, and also genetically and epigenetically, they're slightly different. Actually, they're more different every day that passes than they were the day before. So this seems to apply a little bit cognitively as well. But for personality type, I think they're both very similar broadly, but how they learn is a little bit different for each of them.
I think going into space for long periods of time, having that kind of, like you said at the beginning, having the biological data and matching it up with the cognitive data is going to be really, really fascinating. So in terms of, just briefly, we're going to sort of come to the last couple of hazards. We've gone through radiation and gravity, and this is a hostile and isolated environment. But first, we're going to talk about something which is very close to my heart, because I'm a cereal snacker and I love cake. So Ia, I'm going to start with the question for you. How important is food in keeping the crew happy and focused? And you mentioned at the beginning, it's like having a head cold. So presumably their taste buds are not going to be, the same. And is this going to have a massive impact on the crew?
Totally, absolutely. The food impacts us all the time. And there are special occasions that are planned, and there are surprises planned as well. So, for example, I will talk about the Mars 500 because it was a very good example. So the crew had access for a period of time to a specifically directed diet for to understanding nutrition and its effects and performance. And then they had an opportunity to eat what they want and what they like. And then what happened is that they ran out so we had a Chinese representative on the crew. And there was a celebration that was specific to him. I think it was either Chinese Year or his birthday. And he was so desperate to have noodles, and there were none. There were no noodles. There were absolutely no noodles. But the crew found and they stashed specifically for that spaghetti and made it as similar to his, kind of look like meal.
Yeah.
And that was such a big boost to him. And he talked about it too.
I do think if you're so looking forward, it's like living in another country when you miss the foods from your home country, and then getting to have them is suddenly becomes. Well, I lived in Germany for a while and I missed Yorkshire puddings, and it's just not something that you get in any other country other than the UK. And we had to explain what Yorkshire puddings were to many, many people. And Yorkshire pudding is not that exciting to eat, but when you haven't had it for a year, it's very exciting. And I can imagine people in space experiencing the same kind of thing. So Chris, on that front, if we've got all of this sort of different diet, everything's freeze dried, they're not going to be getting a great deal of fresh fruit and vegetable, I assume. Do you know anything about how that's going to affect their microbiome?
It definitely, we are what we eat. And so we know that we can actually see fragments of even some of the food that they were eating in their saliva when we sequenced the DNA of their saliva. So we could see what didn't all get swallowed yet. It's interesting things like that. We can see also for their stool and particularly their gut microbiome, we can see changes in the diversity of the organisms there, and also particular ratios of two kinds of species called firmicutes to bacteroides we saw shifted. So we know that there's differences that are changing, but we haven't yet done a really interesting experiment where you give the exact same food to all the astronauts and then look at the difference. Some of this has been done for diabetes studies where you can say, okay, we're giving you an isocaloric meal. We know exactly what's in it. You all take the same meal, and then we measure before and after. So that study's not been done yet. So we don't know how much of a factor it is for space, but we know it's definitely a factor on Earth. And so by extension, it's very likely to be, one of the mediating factors of microbiome health. And so for example, like probiotics or yogurt are kind of hard to come by in space, but, lyophilized or dried down probiotics are some you could definitely bring up there and use, but haven't been tried yet.
Well, you mentioned that collecting stool samples, and you can do urine samples and saliva samples. Do you think part of not necessarily the problem, but part of the thing we need to think about going forward, and what do you know about this, is are we lacking tools to do this kind of investigation in space, and are people thinking about developing them?
We have been lacking them for a while. We actually worked with Kate Rubins and others in 2016 to do the first DNA sequencing in space. So you can now take a sample, grab it and sequence all the nucleic acids, the DNA and the RNA right out of it. So we're now entering this era where you can have genomics in space and quickly, take a sample, whether it's a weird microbe growing on the walls of the space station or on your skin, grab it, extract it, and then sequence it and find the answer right away of what's there. So it was an exciting mission to be a part of in 2016. We're replicating this now again this year to do even more sequencing of other things, not just microbes, but also human DNA. So it is, there's new tools up there, which is pretty cool that you can, as a geneticist, it's great to suddenly have all these tools available in space.
And again, genomics in space just sounds so much cooler than just genomics.
Genomics is cool already, but yes, it does. I agree.
I'm gonna leave you with that belief. I'm not gonna jump on board that one because I'm not a geneticist, and I always struggled with it as an undergrad. But I'm gonna hark back very briefly to something you said right at the beginning. So the data you've got at the moment is from these sort of demigod, very healthy, very IQ unique groups of people. Do we think? How much do you trust the data that we have now, or the data that you have now? Do you think it's a skewed population sample? And do you think your N is a bit, like your N for the twin study was essentially 1. Do you think some of these is a bit small and skewed?
Yeah, it's the biggest challenge. And it's called the N problem. The sample size problem is the continual problem for all of spaceflight. And so but that's true for any investigational drug you want to try on a small population. For a rare disease, you might only have 20 of them, and you try what you know based on rationally designed therapies or treatments, and you go for it. And that's what we're doing very much here. So as an N of 2, I guess, because we had one case, one control for the twin study. But what we did is the first thing we did is we took all the molecular and genetic data and compared it to every other patient we've looked at the hospital. So, looked any context of a cytokine or an inflammation marker that would spike. We look at how often that occurred across 200,000 patients from hospitals we have in New York. So it's easy to, the best thing to do when you don't have data is to go get as much data that's as close to it as you can. So that's what we did for the twin study and for other studies, is to go as deep of a dive and as longitudinal of a dive on the individual astronauts, and then also compare it broadly to as much other data from humans and even from animals. There's a project in NASA called Gene Lab, where it's every animal that's ever been flown in space. If there's been any experiments or molecular data, you can download it, play with the data. It's all open for anyone to play with. So that's another thing we compare. Is compared to the mice that fly up and are in 0G and they don't know how to walk, but they float around, and we dissect some of those mice when they land back on Earth as well.
I think what we've established is that space travel is interesting, potentially a little bit dangerous, but not dangerous enough to not do it. So we're going to round everything off with some big picture questions for you guys. So, Ian, I'm going to start with you. What do you think is the most important thing to think about in terms of the long-term effects of space travel on brain health? And are there any great resources that you can point our early career researcher listeners to who might be interested in learning more?
I think it's so important that we explore space outside through space within. And as I'm looking through, the current situation and lockdowns that we've experienced for the last 2 years, you can see that people have gravitated to exploring what happens within, given the external circumstance. And I think people, like never before, experienced what it is like to be isolated. And of course, they have not chosen to do that, like the crew, but I have had a lot of insight for people who have struggled through isolation, through understanding on why the crew do that on purpose, and what works for them and what kind of things that they enjoy doing despite the circumstance. So it is about the world within, the space within, in order to us to be able to go and explore space, the outer space. So I think there's a massive work from psychology and well-being and balancing our perception, because our inner world colors the outer world.
I think that's surprisingly deep. And Chris mentioned earlier Myers-Briggs, and I'm very firmly in the INTJ camp, and I have no issue being shut in a room for weeks on my own. So I would quite enjoy going to space, I think. Chris, same question for you. What do you think is the most important thing to think about in terms of brain health and general health when thinking about long-term space missions?
I think it's being able to have as many things as passively measured as possible. So we have a lot of active tests, blood draws, cognitive tests, but we were expanding more to get things that are wearable devices or things that you don't have to ask someone how they're doing. You can sometimes infer it and measure it, and it's also more reliable data. So I think we've already begun deploying a lot more of them, and more of that's coming. And then just continue to do as many of the molecular measures we can, because when you don't know where to look in the body, the best place is to look everywhere you can. If you're looking for what's changing and what's important and what's the high risk or medium or low risk places. So I think continuing a lot more of the work that we and others have done, and then to do this for many, many more astronauts, and also analog missions on Earth are helpful. Animal models are helpful. Really even learning from any place we can from other clinical trials is helpful. So I think all that and anything else as well.
So Henrik, same question to you. What do you think is the most important thing to think about?
I really would like to explore this brain fluid dynamics problem more. It's very concrete. It's not, and it's a small part of the whole thing. But we have methods to do it, both of course with brain imaging, but that will happen after the space flight. Of course, one could also figure out interesting things of recording such data also in space. But then these types of simple blood biomarkers of brain fluid dynamics and neuronal injury, to find out if this depends on circadian rhythm, microgravity, I shouldn't say that anymore, but anyhow, or if some people are more or less vulnerable to this. I would be very keen. I think that's a perfect PhD student project, actually, if we collaborate on this. And of course, then one needs to link it with brain function and all the things that you talked about, and the devices you mentioned, Chris. It could be such an exciting PhD student project. A little bit high risk, but very exciting.
Well, there's some wonderful live one knockout mice that have altered lymphatic function. I reckon we just send a cohort of them into space with the next set of astronauts and see what happens to them.
But Yvonne, we need to make a mouse which is has a super lymphatic system. We need to remove fluid from brain while you're in space, and how to do that more efficiently. That is what is needed.
Extra pumps, I think.
Extra pumps, opening up the aquaporins.
Exactly. How we do that is another question. That's, again, like you say, that's the next PhD project. I'm going to jump in on that one and say I was here when you had the idea. So one final question. Knowing all we've discussed and all we've talked about in terms of space travel, if NASA called you tomorrow, Henrik, I'm going to start with you because you're on my screen. If NASA called you tomorrow and invited you to go to Mars, would you go?
I would never do that. Never in my life. I am so stuck to Earth. I think Ia would single me out as a person not to put on a space on a spaceship.
Excellent. I love that. You're very self-aware. Well, Ia, if Henrik's definitely not going, do you know yourself well enough? Would you go?
I'm so curious. I'd like to go.
I think that would be my answer too. I just want to see what it's like.
Yeah, I think of course the family is always the factor. So I have young children, and I think that would be a factor for me. But
yeah, leaving them for periods of time.
Yeah, I would definitely go in orbit, and I don't know why they haven't had the psychologist up. I have my suspicions that we will ask too many questions that are uncomfortable.
Yeah, they're going to be worried. They're worried that you're sat in the corner watching them all the time.
Exactly. Yeah, exactly. Yeah. And so I think it's important. And I just wanted to add to Chris's comment about collecting data non-invasively. I think it's so vital because the crew gets so tired of being asked and probed and questioned. And the tool that we're using on voice analysis, which is to detect fatigue, was exactly drawn from that, is not to be invasive and just picking up on something they do all the time. So I think more and more of these tools are coming up, and that will assist us in understanding their well-being.
But I do think that's a very strong argument for having a psychologist up there passively them in the corner. And that way you don't have to ask the questions. You can just sit and make little notes and not tell them what you're writing. Chris, same question to you. Would you go to space on a long space mission?
100%, go right away. My family would prefer I wait a few years. Our daughter is 11, so maybe when she's 18, if I could wait a little bit. But because I wouldn't want to, that'd be a mean thing to do, to die as a father for a young daughter. But I think if could wait a little bit, I'd definitely go then, and would like to go now. Yeah.
I like the fact that Henrik has just said it flat out. No, I'm not going to space. I'm having none of it. I just would be quite curious. I'm on Ia's side though. I think I'd quite like to go up to the International Space Station for a bit of a play around. I'll take mice with me. And then I don't think I'd be so keen to go all the way to Mars. I don't have any plans to learn the sitar, so I think I might go a bit crazy, but you never know, it might be fun. So thank you ever so much, everyone, for joining me today.
Thank you.
It was a pleasure. Thanks.
Thank you very much.
So I'd like to thank today's guests, Professor Christopher Mason, Professor Henrik Zetterberg, and Dr. Ia Whiteley. You've been listening to the Dementia Research Podcast. If you like what you heard today, go back and browse through our archives. Don't forget to like and subscribe at Spotify, Apple Podcasts, or wherever you get your podcasts. I've been your host for the day, Yvonne Couch, reminding you to stay safe and keep researching.
Supporting early career researchers throughout the world and across the galaxy.